Welcome back, networking enthusiasts. Today we'll cover a very interesting topic that is interconnecting multiple sites using WireGuard VPN, but this time we'll use a hub and spoke topology, also called the star topology. I will tell you what hub and spoke topology is and when to use it. Moreover, we won't be using built-in configuration helpers, but set up everything from scratch. To wire it up, we'll use point-to-point tunnels. To make it more interesting, we'll make it dual stack, that is IPv4 and IPv6. I will split this video into two parts. This video will cover the VPN setup with static routes, and in my next video, I will show you how to use Bird Daemon to set up OSPF protocol to advertise our routes between VPN sites to make your network scalable and able to dynamically adapt to changes. My name is Philip. Let's get started. Last time we talked about using WireGuard to build site-to-site VPN in a mesh topology. I suggest watching this video as it covers some of the fundamental concepts. Moreover, that video shows you how to use WG Quick Helper tool that is great to build the tunnels rapidly and is recommended approach for simple topologies. Let's start with explaining what hub and spoke topology is and when to use it. In a full mesh topology, every site is directly connected to every other site. Mesh topologies provide robustness and multiple paths for data to travel, reducing the risk of single point of failure. If the link between node 1 and node 3 goes down, the traffic can still keep flowing via node 2 or node 4. However, the implementation and maintenance of a full mesh can be complex and expensive, as the number of connections grows rapidly. We went from 6 links to 10 links just by adding one more node. Just for that reason alone, a much more common approach is a hub and spoke topology. In this type of network, there is a central node called the hub that all other nodes connect to. If any two nodes want to communicate, this connection needs to go via the hub. There are certain behaviors and properties of such design. First of all, it's simpler to manage and set up, as adding a new node requires provisioning only a single link. That makes the solution more scalable. Moreover, you just modify the configuration on the new node and the hub. You don't touch any other nodes. Furthermore, only the hub needs to have a static public IP. All other nodes can sit behind NAT and can have a dynamic IP that changes from time to time, as we can set up the spoke nodes to always initiate the connection and keep it open. However, because the connection between any two nodes always needs to go via the hub, this particular topology has one major drawback. The hub is a single point of failure. If the hub goes down, all network goes down. If you need to maintain high availability, you can have two hubs interconnected with each other. One will be the primary hub and the other will be the failover hub. Every spoke needs to connect to both primary and failover hubs. If the primary hub goes down, the spokes can use failover hub. If a spoke loses access to the primary hub but still has access to the failover hub, it can reach other spokes via the interconnect between the hubs. If you have only a few sites and don't plan to grow, or if you require high redundancy and fault tolerance no matter the cost, then go for the full mesh topology. On the other hand, if you like to keep it simple or want your network to be scalable, then go for the hub and spoke topology. If you want the best of both worlds, then go with the concept of two hubs interconnected with each other and spokes that are interconnected to those hubs with two links. Let's briefly describe our network topology. We have three nodes spread across different locations. One is in a central location and is called the hub. They are all connected using 192.168.10/24 that we call the public network. Additionally, node 1 has 10.1 private network attached and node 2 has 10.2 network and 10.3 private networks connected. We'll set up a VPN network from 169.254/16 range that's dedicated link local address space that is not used for any other purpose on the internet. This makes it a good choice for point-to-point endpoints because it's guaranteed to be unique and there is no risk of conflict with another networks. This time we won't be interconnecting every node with each other in a mesh, but instead we'll create only two point-to-point VPN tunnels. With this approach, for every new site, we just add one more tunnel with the hub, and that's it. First tunnel will connect node 1 with the hub, and the second tunnel will connect node 2 with the hub. Node 1 will have .2 IP, node 2 will have .3 IP, and the hub will have .1 IP. Because those are point-to-point links, we can reuse the same IP on both interfaces. Point-to-point links interconnect only two servers, hence you don't have to assign IPs from the same subnet, like you do in a standard broadcast network. Moreover, on a point-to-point link, people often use so-called unnumbered IPs, that is, borrow from a different interface on the same host. But this is a topic for a separate video. What we want to achieve is network reachability between VMs sitting in 10.x private networks. We want the traffic between our private networks to be tunneled over the public network. Mind that this time the VPN traffic between node 1 and node 2 goes via the hub that centralizes all the inter-node communication. One of WireGuard's great features is its native support for IPv6. Let's quickly go through our IPv6 network address scheme. Important thing to mention is that all three servers are interconnected with an IPv4 network. WireGuard is capable of tunneling IPv6 traffic over IPv4 network and the other way around. You can tunnel IPv4 traffic over IPv6 network. In our example, we'll be tunneling both IPv4 and IPv6 traffic over the IPv4 network. Let's start with defining our private networks. For that purpose, we'll use the FD00/8 prefix that is reserved for unique local addresses. This is similar to IPv4 private addresses 10/8, 172.16/12, and 192.168/16. This prefix is meant for local communication only. Node 1 has FD01/64 private network, and Node 2 has FD02 and FD03/64 private networks. For tunnel endpoints, we'll use FE80/10 prefix that is dedicated for IPv6 link local. Our hub will have :1 IP, Node 1 will have :2 IP, and Node 3 will have :3 IP. IPv6 link local addresses are ideal for point-to-point communication. Let's get to business. To speed up the configuration, some of the tasks will be executed at all three nodes at the same time. First, we'll update our packages list with apt-update, and then install WireGuard with apt-install. WireGuard mimics SSH, so for every host you need to create a public and private key. For that to happen, let's go to WireGuard configuration directory, set umask to 077 so that our newly created keys will have read-write permissions only for the owner. Then let's generate the keys with the following one-liner. WG key will generate the private key and print it to the standard output. We'll pipe it to the T command that will store the private key to the file and print it to the screen. The WG key command accepts the private key and prints the corresponding public key, which will redirect to a file. Okay, keys have been created. Similar to SSH, the idea is to share the key with other party so that it can use the key to authenticate and encrypt data. Unlike other VPN technologies, WireGuard is not responsible for distribution of keys. Like in SSH, you need to exchange your keys out of band. Next, we need to configure our VPN interfaces. First, we'll set up the WG0 interface on the hub. That will be the interface pointing towards node 1. I will name the file wg0conf as that will be the VPN interface name on our node. We'll start with the interface section that specifies configuration values for our VPN interface. First, we need to specify the private key for the interface. Let's load it from the file that we've just created. Then let's specify the UDP listen port that our server will listen on. Please mind that WireGuard encapsulates the traffic inside UDP packets. Our interface section is ready. This time we won't be using WG quick script helper, but we'll configure WireGuard for the command line, hence we don't specify the local peer address in our configuration file. We'll configure peer's IP later using the IP command. Now let's define our peer, that is node 1. We'll start with the peer section that defines the remote servers that we'll be connecting to. First thing we need to provide is the public key for the remote server. In our case, it will be the node 1's public key. Then we'll specify the remote endpoint. That is an optional field that specifies to which IP and port to send the packets to for a particular peer. If your remote site has a dynamic IP or is behind a NAT and you cannot do port forwarding, then you can omit this field. You'll specify that option on node 1 so that it will be the one that establishes the tunnel. Mind that at least one end needs to have this field defined. In our case, HUB and Node 1 both have static IPs and full reachability, so I'll define the endpoint on both, pointing to each other. Here, let's provide the IP and port of Node 1. Endpoint will be automatically updated to the IP and port of the correctly authenticated packets. This allows the nodes to roam. Lastly, the allowed IPs parameter specifies the comma-separated list of IPs or ranges that the incoming packet for this peer is allowed and to which outgoing traffic is directed. In the basic case, you'd specify the private network sitting behind node 1. However, we want to set up a dynamic routing protocol to exchange our routes and be able to add new networks without reconfiguring our tunnel. For that purpose, I will provide quad 0/0 to allow all IPv4 traffic via the tunnel and /0 to allow all IPv6 traffic over the tunnel. I will jump to node 1 to set up the remote end of the tunnel. In the interface section, we'll load node 1's private key and specify the UDP port that server will be listening on. In the peer section, we'll define the public key of the remote end, that is the hub. We'll specify the IP and port that the remote end, that is the hub, is listening on. And finally, allow all traffic to flow via the tunnel. Let's quickly go over our VPN configuration one more time. At the top we have our hub, at the bottom we have node 1 remote site. Private key of the hub, private key of node 1. UDP listening ports. They could be different, but I did keep them the same for consistency. Public keys that we did exchange, so that hub has node 1's public key and node 1 has hub's public key. Endpoint inside the hub configuration is pointing to node 1 IP and node 1 listening port. Endpoint inside the node 1 configuration is pointing to the hub IP and hub listening port. Finally, let's bring the tunnel up. We won't be using WG Quick Helper script, instead we'll set it up from scratch. First step is to create a WG0 interface. We'll use the IP link add device command, followed by the interface name, that is WG0, followed by the interface type, that is WireGuard. Our server has a new WG0 interface. One thing to notice is MTU set to 1420. That's 80 bytes less than for underlying Ethernet. 20 byte is IP header, 8 byte is UDP header, and the rest is WireGuard. I will create a separate video on fine-tuning the MTU. Let's go with the default for now. Our interface is there, so let's assign some address to it. On the hub, I will use the IP address add command and specify the 169.254.0.1 IP for the interface. As we are setting a point-to-point link, let's specify the peer keyword and put the IP of remote end, that's node 1, and set it to 169.254.0.2. The device will be WG0. Let's also set the IPv6 IP for the interface to FE80:1/64. Let's double check if the IPs have been assigned. All looks good. Now I'll repeat the same steps on node 1. Let's add the IPv4 address of 02 with 01 peer. Let's add the IPv6 address of FE80:2/64. Let's check if the IPs have been assigned. Now let's set our WireGuard configuration of WG0 interface with wgsetconf command, followed by the interface name and the path to the configuration file. Finally, let's bring the VPN connection up with IP-link set command. Let me test if our point-to-point link works by pinging the remote peer's VPN address using its IPv4 address. Connection works. Let's try pinging the remote end of the tunnel via its IPv6 address. Connection works. We can also check the status of our tunnel with the WG command. This will give you all the details about your WireGuard configuration. Interface name, hub's public key and listening port, Node1 peer public key and remote IP endport. Time since last traffic seen on the tunnel, as well as how much traffic was sent and received. Mind that in its default configuration, that is without the keep alive set, WireGuard won't send any traffic unless needed. WireGuard is not a chatty protocol. Let's summarize where we are at. We have a point-to-point VPN tunnel established between Node 1 and the hub. We have IPv4 reachability between 169.254.0.2 and 169.254.0.1 that are our VPN IPv4 addresses. We also have IPv6 reachability between FE80:1 and FE80:2 that are our VPN IPv6 addresses. Mind that IPv6 traffic is tunneled inside IPv4 packets. Let's quickly repeat the same steps to build a tunnel between the hub and Node 2. Remember that we are building a totally separate VPN tunnel. It will have a separate network interface on the hub and separate UDP listening port. You may ask why we cannot reuse the existing WireGuard endpoint and just connect to the same port on the hub from both Node 1 and Node 2, like we did in the mesh topology. We need two separate interfaces because allowed IPs that's used to define IP ranges for routing cannot overlap. You could get away with a single VPN interface on the hub if you would open the hub configuration, put 10.1 network in the allowed IPs for Node 1 peer, and 10.2 as well as 10.3 network in the peer configuration for Node 2. In other words, you would have to explicitly define mapping between the peer and the allowed IPs. Because we don't want to limit ourselves to certain IP ranges allowed via the tunnel, we need to create a separate VPN tunnel with a new interface. First, I will go to the hub and copy the WG0 configuration to WG1. Let's open the WG1 configuration file that will hold the second tunnel configuration. We'll update the listening port to 60,032. We cannot use 60,031 as it's already occupied by the other tunnel. Then let's update the endpoint IP with Node 2 address. Let's also update the configuration with the Node 2 public key. Now let's set up the other end of the tunnel, that's Node 2. First, let's set the listening port, load the private key, and define our peers, that's the hub. I'm providing hub's public key. Setting the endpoint to hub's IP and allowed IP to quad 0 for IPv4 and :0 for IPv6. Let's start the tunnel. I'm creating a new WG1 interface, setting up addresses for point-to-point tunnel. I'm reusing the same IP on WG1 as on WG0 as its point-to-point link. Loading WireGuard configuration for WG1 interface and bringing the link up. Let's repeat the same steps on the other end of the tunnel, that's Node 2. The tunnel should be up. Let's ping the hub IPv4 address from Node 2 via the tunnel. Let's test the connection using an IPv6 address. Our point-to-point connection works. If we go back to our hub and retrieve WireGuard configuration with WG command, we can see two tunnels up. WG0 pointing to Node 1 and WG1 pointing to Node 2. Because allowed IP's parameter is set to quad 0 on both links, you can securely route any network via those tunnels. Now let's set up some static routes just to prove that the connectivity is there. I will start by enabling packet forwarding for IPv4 and IPv6. This is a mandatory step. Now let's add the static route to 10.1 network that is reachable via the WG0 interface pointing towards node 1. Because this is a point-to-point link, we don't have to specify the next hop IP. We just specify the interface that the packet should go out with. In point-to-point links, there is no other way to send the traffic but to send it to the peer IP. 10.2 and 10.3 networks are reachable via WG1 interface pointing towards node 2. Let's add those routes as well. Okay, our hub is ready to route traffic. Let's go to node 1 and add routes to 10.2 and 10.3 private networks via WG0 interface pointing towards the hub. Let's go to node 2 and add a route to 10.1 private network via WG0 interface pointing towards the hub. If we check the routing for 10.1 network, we can see that the hub will use WG0 interface pointing to node 1. Node 1 has this network directly connected via ETH2. Node 2 will use WG0 interface pointing to the hub. If we check the routing for 10.2 network, we can see that this time hub will use the WG1 interface pointing to node 2. Node 1 will use WG0 interface pointing to the hub, and node 2 has this network directly connected via ETH2. Now it's time for some tests. There are 3 VMs, one in each private network. Let me ping VM2 from VM1. Works. Let's trace the connection. The traffic first goes to node 1, which is the default gateway for VM1. Then it goes to the hub. From there, it goes to node 2 and finally reaches VM2. Let's confirm IPv6 connectivity as well. For that, we need to add static IPv6 routes. On the hub, we'll add the route towards FD01 network via WG0 interface pointing towards node 1. And route towards FD02 and FD03 networks via WG1 interface pointing towards node 2. On node 1, we'll add the route towards FD02 and FD03 network via WG0 interface, pointing towards the hub. On the node 2, we'll add the routes toward FD01 network via the WG0 interface, pointing towards the hub. Now let's do some IPv6 connectivity tests. There are 3 VMs, one in each private network. VM1 with FD01::2 IP, VM2 with FD02::2 IP, and VM3 with FD03::2 IP. I'll go to VM1, check its IP address. Now let me ping VM2. Works. Let's trace the route to VM2. First, the traffic goes to node 1 as it's the default gateway. Then it drops on the hub as we are using link local addresses. Next we have node 2 IP and finally VM2. We have our setup ready with 2 sites connected with WireGuard in a hub and spoke topology using static routes. In part 2 of this video, I will show you how to get rid of static routes and use OSPF to dynamically advertise our networks.